Early astronomers struggled to understand why constellations trace perfect circular arcs instead of darting straight into the void. Newton recognized an object's natural tendency is traveling in a straight line. Maintaining a circular orbit requires an inward pull that constantly redirects momentum. Our internal senses tell a different story. Entering a roller coaster loop, you feel pressed outward against your seat, shoved away from the center. This captures the conflict between perspective and physics. Outside looking in, the track clearly pushes the rider toward the center. Inside the coaster, the rider experiences the illusion of centrifugal force, an outward push appearing only because the perspective is spinning. Physics defines this center-seeking requirement with a specific equation: mass times velocity squared divided by the radius. Squaring the velocity means a small increase in speed demands a massive increase in force, especially as you shorten the radius of the turn. We can apply this to a 900-kilogram car taking a curve with a 500-meter radius at 25 meters per second. By multiplying the mass by the velocity squared and dividing by the radius, we find the result: 1,125 newtons of inward force. Centripetal force is a category filled by other physical interactions. In this car, friction provides the pull. In an atom, electrostatic attraction keeps the electrons in place. Ernst Mach looked at these forces through the lens of reference frames, suggesting inertia itself is tied to the distribution of matter across the universe. Industrial centrifuges utilize these principles to separate substances. In the rotating frame of this spinning chamber, denser substances move outward, appearing to obey a centrifugal force that does not exist to an outside observer. Distinguishing between a stationary viewpoint and a spinning one dictates whether you treat centrifugal force as a mathematical correction or a sensory distraction. On a flat road, safety depends entirely on the friction between rubber and asphalt. When rain or ice lubricates the surface, the tires lose the ability to provide inward pull. Engineers account for this by banking the road. Tilting the surface reorients the normal force, the ground's perpendicular push, so that it contributes to the inward centripetal requirement. Imagine a curve with zero friction. Using only the car's weight and the angle of the bank, can you determine which part of the normal force keeps the car on the track? Pause here to sketch your diagram. The normal force resolves into two vectors. The vertical component balances the car's weight, while the horizontal component, n sine theta, provides the necessary inward force to navigate the curve. Combining these equations allows the car's mass to cancel out. The resulting formula shows that the ideal speed for the turn is determined only by gravity, the radius, and the angle of the bank. Banked roads demonstrate that centripetal force can be satisfied without relying on friction. By angling the surface, engineers redirect the car's own weight to provide the necessary inward pull. These laws apply to a satellite orbiting the Earth. In the vacuum of space, there is no friction or tilted road to hold the craft in place. In planetary motion, gravity acts as the centripetal force. It provides the constant inward tug that prevents the satellite from flying away in a straight line. We can calculate the required speed by setting the law of universal gravitation equal to the centripetal force formula. The mass of the satellite cancels out on both sides. This shows that every object at a specific altitude, regardless of its weight, must travel at the same velocity to maintain a stable orbit. This summary clears the confusion. Centripetal force is the real center-seeking force required by the laws of motion. Centrifugal force is the apparent outward sensation felt within a spinning frame.